What if you could turn a piece of coal into a priceless gemstone, or sterilize medical equipment using nothing but sheer force? We are bridging the gap between heavy-duty machinery and molecular transformation by harnessing millions of pascals of pressure. Explore the incredible science of synthetic growth and see how extreme physics is shaping the future of industrial technology. The mastery of immense pressure represents one of the most profound and transformative achievements in the entire history of industrial engineering. At its very core, the ability of modern civilization to generate, harness, and control unfathomable compressive forces relies entirely upon a fundamental principle of fluid mechanics, first articulated by the brilliant French mathematician and physicist Blaise Pascal in 1653, and subsequently published a decade later. Pascal's principle, or the law of transmission of fluid pressure, dictates a seemingly miraculous reality of physics. A pressure change applied to any point within a confined, incompressible fluid is transmitted completely undiminished throughout the entirety of that fluid, such that the exact same change in pressure occurs everywhere, striking the walls of its container with equal magnitude. Because liquids like hydraulic oil or water possess essentially zero compressibility under standard mechanical constraints, they act as flawless conduits for kinetic energy. In mathematical terms, pressure is defined as the total force applied divided by the total area over which it is distributed. Therefore, if an external force is applied to a small input piston, the resulting pressure is universally transferred to a significantly larger output piston. While the pressure remains absolutely constant across the system, the sheer mechanical force is multiplied exponentially in direct proportion to the expanded surface area of the larger piston. This elementary but devastatingly effective physical law ensures that a relatively minuscule input force can effortlessly lift heavy vehicles, bend high-tensile steel, or crush solid boulders, provided that the conservation of energy is strictly maintained through a proportional increase in the distance the input piston must physically travel.
In the contemporary industrial landscape, this centuries-old principle powers machines of truly staggering scale and breathtaking capability. Modern manufacturing relies heavily on these hydraulic leviathans to physically shape the modern world, hammering out everything from commercial aerospace components to the lightweight chassis of next-generation electric vehicles. As of 2026, the automotive manufacturing sector continues to represent the single largest demographic of hydraulic press demand in the United States, single-handedly accounting for 34% of the entire market. This is closely followed by the aerospace and defense sectors, which account for 26%, the industrial machinery sector at 22%, and plastics processing at 18%. Within these colossal, heavy industrial facilities, average press capacities regularly exceed 1,200 tons of raw force, completely dwarfing the capabilities of historical manufacturing tools. Global pioneers in advanced metal-forming technology, such as the historic German-based Schuler Group and the Canadian heavy-duty manufacturer Macrodyne Technologies, have relentlessly pushed the boundaries of mechanical engineering to unprecedented extremes. Today, they produce custom turnkey servo-hydraulic presses that are genuinely capable of exerting up to 30,000 tons of continuous force. These gargantuan machines are no longer blunt instruments. They've evolved into highly sophisticated computer-controlled systems, often integrated with Allen Bradley control software and fully automated robotic loading arms that boast microscopic positioning accuracies to within 0.05 millimeters. Operating as the vital, irreplaceable workhorses of the deep drying, stamping, forging, and powder compaction industries, these presses utilize advanced fluid dynamics and massive hydraulic cylinders to uniformly distribute compressive force across broad surface areas, allowing for the flawless, precise deformation of high-tensile metals, resilient plastics, and highly advanced composite materials. Yet the raw, macroscopic kinetic power of these hydraulic systems has recently transcended the restrictive confines of the factory floor to capture the intense fascination of the global general public. Through widespread internet phenomena, viral video compilations, and highly successful educational media, audiences worldwide have been entirely captivated by real-world, high-definition footage of heavy-duty industrial presses violently crushing incredibly high-density materials. Dedicated media platforms, such as the immensely popular hydraulic press channel and its spin-off Beyond the Press, utilize heavily modified 150-ton industrial presses equipped with state-of-the-art Chronos high-speed cameras capable of recording at 1,500 frames per second and massive 240-ton force sensors to pulverize everything from everyday household objects to incredibly dense industrial alloys. These dramatic, incredibly visceral demonstrations serve as a highly accessible, real-time education in advanced materials science, yield strength, and the terrifying realities of kinetic energy. When relatively soft elemental metals, such as pure aluminum, tin, or lead, are subjected to these immense vertical loads, their uniform hydraulic pressure overwhelms their atomic lattice structures almost instantaneously, causing the solid metals to dramatically deform, flow, and flatten with the fluid, squishy consistency of children's modeling clay.
However, when exceptionally high-density ceramics, exotic superalloys, or refractory metals are introduced to the hydraulic anvil, the true astonishing limits of mechanical force are spectacularly revealed. In widely documented and incredibly popular experiments involving objects made of solid tungsten and tungsten carbide, materials universally renowned for their extraordinary density, unmatched atomic rigidity, and immense refractory properties, the application of nearly 150 tons of continuous hydraulic force barely manages to alter the shape of the test subject. Instead of yielding or flattening under the tremendous load, the kinetic energy is transferred directly downward into the machine itself, causing the indestructible tungsten cube to literally sink into and permanently deform the hardened steel base of the press. Other dramatic experiments involve freezing dense elemental cubes in liquid nitrogen or attempting to crush specialized cyanide-tipped tungsten discarding sabot rounds, demonstrating not just the force of the machine, but the astonishing resilience of specific atomic structures. Understanding and mastering this raw macroscopic power is the necessary first step toward a much more sophisticated and awe-inspiring scientific goal: the deliberate manipulation of matter at a fundamental, molecular, and atomic level. The evolutionary transition from crushing large blocks of steel to actively altering the foundational properties of chemical elements requires a massive conceptual shift from industrial giantism to highly calibrated, high-pressure microphysics. When pioneering scientists pushed the boundaries of pressure into the megabar and multi-megabar range, reaching millions of atmospheres of compression using specialized equipment like diamond anvil cells, they are no longer merely reshaping the external geometric contours of a material. They are fundamentally altering the energetic interactions, bonding characteristics, and quantum states of the atoms themselves. Under normal atmospheric conditions, chemical intuition heavily relies on established rules of electronegativity, standard reactivities, and the predictable filling of atomic orbitals. However, sophisticated high-pressure X-ray crystallographic studies have revealed that intense, sustained compression initiates three profound mechanisms within solid matter: bond compression, bond angle bending, and intermolecular compression. As atoms are violently forced into spatial proximity significantly smaller than their natural equilibrium distances, the physical overlap of their electron orbitals induces massive electronic shell collapse and widespread electron delocalization. Under such extreme, unfathomable stress, the foundational Aufbau principle of orbital filling is actually strengthened, but the traditional energy ordering of those electron shells shifts dramatically, entirely redefining the established electronegativity of the elements, to the point where scandium and titanium unexpectedly become the most electropositive elements. Materials that act as reliable insulators at room temperature are forced to behave in entirely alien ways. For instance, high pressure can trigger structural rearrangements that increase the coordination number of atoms, forcing quartz to transform into a much denser structure known as stishovite, and compelling common pyroxene minerals to transform into dense perovskite structures. Even more astonishingly, the application of millions of pascals of pressure fundamentally confirms the 1928 prediction by J.D. Bernal that absolutely all matter will ultimately transition to a metallic state if compressed with sufficient force.
Nitrogen, the highly stable, non-reactive diatomic gas that constitutes nearly 80% of the Earth's atmosphere, undergoes a profound pressure-induced phase transition when subjected to the intense conditions mimicking the deep interiors of planets. At these extremes, the nitrogen molecules violently dissociate into an extended, complex polymeric network, transforming into a brilliant, electrically conductive metallic fluid. By successfully scaling the basic principles of industrial hydraulic compression down to the sub-microscopic quantum realm, humanity has unlocked the unprecedented ability to forge entirely new phases of matter, executing acts of industrial alchemy that redefine the very boundaries of material science and quantum chemistry. Perhaps no application of high-pressure technology is more deeply rooted in the collective public imagination or more historically significant to material science than the successful laboratory synthesis of diamonds. For millennia, the creation of these flawless, brilliantly reflective, pure carbon crystals was considered strictly the exclusive domain of deep geological time and the unfathomable, chaotic forces churning within the Earth's mantle. Located approximately 100 miles beneath the Earth's fragile crust, the mantle provides the precise, unforgiving combination of extreme geothermal heat and crushing hydrostatic pressure required to force loose carbon atoms into a tightly packed, highly rigid cubo-octahedral crystalline lattice. The human quest to artificially replicate this subterranean alchemy culminated on a historic winter day, December 16, 1954, when an American physical chemist named H. Tracy Hall, working on the highly secretive Project Super Pressure at the General Electric Research Laboratory in Schenectady, New York, successfully manufactured the first truly reproducible synthetic diamond. Utilizing a revolutionary high-pressure, high-temperature apparatus of his own design, a machine that would eventually be designated as a historic mechanical engineering landmark by the American Society of Mechanical Engineers, Hall subjected a careful mixture of powdered carbon and iron sulfide to sustained pressures reaching an astonishing 100,000 atmospheres and blistering temperatures of 1,600 degrees Celsius. The inclusion of a metallic catalyst, specifically tantalum discs that also conducted electricity to heat the cell, was the critical conceptual innovation that significantly lowered the activation energy required for the carbon to successfully crystallize. After roughly 38 minutes of sustained, terrifying compression, the apparatus was cooled and cracked open, revealing true, sparkling octahedral diamond crystals firmly attached to the tantalum. This monumental scientific achievement definitively proved that the fundamental mechanical forces of planetary geology could be safely contained and manipulated within a laboratory setting, effectively birthing a massive synthetic diamond industry that currently produces millions of carats annually, both for industrial and aesthetic applications. Today, this incredible legacy lives on in the modern high-pressure, high-temperature HPHT process, which is a highly advanced, technologically refined descendant of Hall's original pressure cooker method. The contemporary HPHT process meticulously mimics the extreme environment of the deep Earth to continuously grow both flawless industrial abrasives and exceptionally large gemstone-quality diamonds. The process begins when a tiny, highly pure diamond seed is placed within a specially designed mechanical press alongside a highly purified carbon source, which is most typically high-grade graphite.
The massive growth chamber is then subjected to staggering pressures fluctuating between 5 and 6 gigapascals, which is equivalent to roughly 1.5 million pounds per square inch, and heated to temperatures ranging between 1,300 and 1,600 degrees Celsius. Under these extreme simulated geological conditions, a metallic flux catalyst composed primarily of iron, nickel, or cobalt reaches its melting point and actively dissolves the graphite carbon source. The free-floating carbon atoms then slowly migrate through the highly pressurized molten flux toward the slightly cooler diamond seed, where they precipitate and crystallize layer by layer over the course of 1 to 2 weeks to form a significantly larger pure diamond crystal. The HPHT method is uniquely capable of producing diamonds with a complex cubo-octahedral growth habit that is structurally identical to natural stones mined from the earth, and it remains the absolute preferred technique for synthesizing highly vibrant, fancy-colored diamonds, such as vivid yellows and deep blues, where the brilliant hues are a natural consequence of the high-pressured growth environment and elemental incorporation, rather than artificial secondary irradiation. However, the global diamond industry in the year 2026 is undergoing a massive, disruptive technological shift with the rapid maturation and widespread commercialization of chemical vapor deposition, or CVD techniques. While the traditional HPHT method relies on the sheer, brute physical force of extreme compression to aggressively mold carbon, the CVD process represents a vastly more elegant, highly engineered bottom-up approach that meticulously manipulates matter in a low-pressure, highly controlled vacuum environment. In the sophisticated CVD process, ultra-thin, highly polished diamond seed plates are carefully placed inside a sealed vacuum chamber that is subsequently flooded with a carefully calibrated carbon-rich gas mixture, almost exclusively consisting of methane and hydrogen. Instead of utilizing immense hydraulic pressure, intense microwave beams are utilized to heat the localized gases to temperatures ranging from 700 to 1300 degrees Celsius, converting the volatile gas mixture into an energized, glowing plasma state. The intense energy of this plasma systematically breaks down the complex molecular bonds of the methane gas, liberating individual carbon atoms that then gently rain down and deposit directly onto the seed plates, bonding atom by atom in a perfectly flat, layered tabular formation. Historically, the CVD process faced significant, seemingly insurmountable challenges regarding its overall growth rates, typically achieving only a meager 1 to 10 micrometers of single crystal growth per hour, which severely limited its commercial viability against the faster HPHT presses. But by 2026, comprehensive industry-wide optimizations in complex gas phase chemistry, highly advanced multi-frequency plasma dynamics, substrate preparation, and sophisticated thermal management systems have allowed cutting-edge manufacturers to target sustained, flawless growth rates exceeding 100 micrometers per hour. While HPHT technology still retains a slight economic pricing advantage for producing exceptionally large stones over 2 carats due to the massive energy costs and the extreme difficulty of maintaining massively scaled high-pressure chambers, CVD has rapidly become the completely dominant force for modern industrial applications. When examined by expert gemologists, advanced identification techniques involving intense phosphorescence and polarized light analysis quickly reveal the differences between the two methodologies. HPHT diamonds frequently exhibit extremely strong orange or yellow phosphorescence and cross-shaped fluorescence patterns, whereas CVD diamonds showcase greener, less intense phosphorescence and highly distinct banded strain patterns resulting from their layered growth. Most importantly, however, CVD consistently produces pristine Type 2A diamonds, meaning they are completely free of the microscopic metallic flux inclusions that occasionally plague HPHT stones. While 80 to 90% of CVD diamonds still require post-growth HPHT annealing to correct slight brownish tints caused by structural strain during the rapid growth phase, their ultimate absolute structural purity is the driving force behind the most significant pivot in the synthetic diamond market, the rapid transition from luxury jewelry to critical foundational hardware for next-generation quantum processors. As the global semiconductor industry rapidly faces the absolute physical and thermal limitations of traditional silicon, synthetic single-crystal diamonds are decisively emerging as the ultimate irreplaceable 21st century material. A defining characteristic of the 2026 technology landscape is the massive global integration of laboratory-grown diamonds into high-frequency electronics and highly sensitive thermal management systems. With a measured thermal conductivity vastly exceeding 2,000 watts per meter Kelvin, synthetic diamond is unequivocally the most efficient heat sink material known to modern science. As massive hyperscale data centers, advanced artificial intelligence clusters, and high-performance electric vehicles demand increasingly powerful, densely packed electronic components, ultra-pure CVD diamonds are being aggressively deployed as thermal interface materials to draw devastating system-destroying heat away from fragile microprocessors, allowing them to run substantially faster, significantly cooler, and vastly more efficiently than previously thought possible. Beyond mere thermal management, these flawless lab-grown crystals are serving as the absolute foundational substrate for the future of highly secure networked quantum computing. In a major historic milestone for the creation of scalable quantum devices, researchers from leading academic institutions spanning Cambridge, Oxford, and Manchester, working alongside commercial quantum computing firms like IonQ, have achieved unprecedented pinpoint control over individual quantum defects within synthetic diamond crystal lattices. By carefully and deliberately injecting single atoms of elements such as tin, silicon, or germanium into the carbon structure during the highly controlled chemical vapor deposition, scientists create what are known as Group 4 color centers or tin vacancy defects. These deliberate microscopic atomic imperfections are incredibly prized for their high degree of symmetry, acting as highly stable spin-photon interfaces. This profound capability means they can successfully store quantum bits of information, qubits, in the spin of a single trapped electron and flawlessly transmit that highly complex data across a network by individual particles of light. In a groundbreaking, paradigm-shifting commercial leap, leading manufacturers, including Element 6, have developed foundry-compatible, quantum-grade diamond thin films that can be bonded directly onto standard semiconductor substrates like silicon and silicon nitride. This incredible breakthrough utterly shatters previous manufacturing limitations, allowing for the industrial-scale, trillion-dollar mass production of diamond-based quantum memories, sensor arrays, and photonic interconnects, using highly established semiconductor fabrication techniques. By networking multiple quantum processing units together through these diamond-enabled photonic links, the industry is effectively moving quantum networks out of the isolated, hyper-cooled laboratory and into a massively scalable commercial reality capable of executing extraordinarily complex algorithms. By forcing carbon to completely transcend its natural geological limits, human engineering has brilliantly transformed the basic building blocks of a decorative gemstone into the very engine of the impending quantum age. The profound engineering expertise and metallurgical mastery required to safely contain millions of pascals of pressure within the confines of a controlled laboratory are equally, if not more vital, when fragile human beings attempt to survive those exact terrifying pressures in the unforgiving natural world. The deepest, most isolated regions of the world's oceans, collectively known as the Hadal Zone, began at staggering depths of 6,000 meters and plunge violently downward to nearly 11,000 meters at the absolute bottom of the Challenger Deep within the Mariana Trench. This abysmal, alien realm represents one of the most relentlessly hostile and deeply mysterious environments on the entire planet, characterized by absolute impenetrable darkness, near freezing ambient temperatures, exceptionally low food availability, and most significantly, an overwhelming ubiquitous hydrostatic pressure that reaches a hull-crushing 16,000 pounds per square inch, or roughly 1,100 bar.
For many decades, the staggering, crushing weight of the ocean severely restricted human access to the seafloor, making the Hadal Zone statistically less visited than the surface of the moon. Early, heroic phases of exploration relied on incredibly cumbersome, highly dangerous vessels like the historic bathyscaphe Trieste, which achieved its necessary buoyancy through the use of a massive, incredibly vulnerable tank filled with thousands of gallons of highly flammable aviation gasoline.
While the gasoline created an internal atmosphere that kept the submarine's steel sphere from instantly collapsing, it made the vessel exceptionally awkward, incredibly dangerous, and practically impossible to maneuver along the dark, entirely unknown topography of the jagged seafloor. Modern oceanic exploration, however, demands highly repeatable, impeccably safe, and incredibly maneuverable access to the deep ocean, necessitating a radical, uncompromising evolution in deep-sea pressure technology, advanced material science, and submersible design. Navigating the immense life-or-death engineering challenges of successfully building a human-occupied submersible capable of withstanding the unimaginable weight of the Hadal Zone requires an absolutely uncompromising approach to materials science and structural geometric perfection. The dire consequences of inadequate engineering in this unforgiving environment were tragically highlighted by the catastrophic loss of the OceanGate Titan submersible, which suffered a fatal implosion due to critically flawed safety practices, a refusal to adhere to third-party classification testing, and the dangerous use of experimental carbon fiber materials that suffered from severe delamination and fatigue loads after repeated pressurization cycles. In stark contrast to experimental hubris, the defining, triumphant achievement in modern ultra-deep-sea engineering is the Triton 36002, famously known as the Limiting Factor, a bespoke submersible commissioned by explorer Victor Vescovo for the incredibly ambitious 5 Deeps expedition. To completely protect its crew of 2 from the lethal, instantaneous forces of the deep, the vessel relies heavily on a perfect spherical pressure hull, painstakingly forged from highly advanced, high-strength titanium. Titanium is the absolute optimal natural choice for this extreme application because it offers an exceptionally high strength-to-weight performance ratio while remaining completely and utterly impervious to the corrosive, degrading effects of salt water. The geometry of the hull is equally, if not more critical than its metallurgical composition. Deep-sea engineers implicitly understand that hydrostatic pressure must be distributed perfectly, universally evenly across the entire surface area. Any slight deviation from a perfect sphere or the introduction of shapes with sharp edges creates deadly points of concentrated stress that rapidly lead to catastrophic material fatigue and instantaneous implosion. Consequently, the massive titanium hemispheres of the Limiting Factor, forged by ATI in Cudahy, Wisconsin, using a 15,000-ton hydraulic press, were meticulously machined to within an astonishing 99.933% of true flawless spherical form. Furthermore, to completely eliminate the microscopic vulnerabilities, heat-affected zones, and metallurgical inconsistencies inherently created by welding, the 2 halves of the massive 90mm thick hull were assembled using a highly proprietary clamping and bolting mechanism, ensuring absolute structural homogeneity throughout the entire pressure vessel.
To guarantee unquestionable safety, the hull was subjected to horrific pressures of 1,400 bar inside the world's largest hyperbaric chamber at the Krylov Institute in Russia, significantly exceeding the maximum pressure found at the very bottom of the ocean, earning it an unprecedented, unlimited depth commercial certification from the DNV-GL Classification Society. To achieve the necessary critical buoyancy without resorting to the immense bulk of highly flammable gasoline tanks, modern submersibles envelop their titanium cores in highly advanced syntactic foam, a remarkable composite material consisting of billions of microscopic hollow glass spheres permanently suspended in a rigid epoxy resin, providing massive, reliable lift while remaining almost entirely immune to deep-sea compression. This flawless, highly redundant integration of deep-sea pressure technology not only ensures human survival in the most hostile environment on Earth, but also allows scientists to conduct totally unprecedented, groundbreaking studies of the incredibly complex Hadal ecosystem. The deep ocean is not a barren, lifeless wasteland as previously assumed, but a remarkably vibrant habitat, absolutely teeming with highly specialized piezo-philes,
unique microorganisms biologically adapted to not merely survive, but thrive under extreme hydrostatic pressure, as well as strange bioluminescent life and incredibly complex, nutrient-rich ecosystems surrounding superheated volcanic hydrothermal vents.
However, studying these bizarre macroorganisms presents a highly unique, deeply frustrating biological challenge. Bringing them to the surface subjects them to a rapid, lethal reduction in ambient pressure, completely destroying their fragile cellular structures and native morphology before they can be properly analyzed by marine biologists. To decisively solve this problem, brilliant mechanical engineers have recently developed highly complex, full ocean depth macroorganisms pressure-retaining samplers, or FOMDOPS. These highly sophisticated, incredibly durable robotic instruments are mounted directly on the submersible's external mechanical arms and are explicitly designed to capture sediment and delicate biological samples at maximum depths of 11,000 meters. Utilizing incredibly advanced pressure compensation mathematics, these brilliant titanium cylinders firmly seal at the seafloor and utilize heavily sprung hydraulic pistons and precision check valves to dynamically compensate for the expansion and inevitable deformation of the metal casing during the long, slow ascent through the water column. Rigorous high-pressure chamber simulations and real-world deployments in the West Philippine Basin have thoroughly verified that these devices can successfully maintain massive internal pressures of 105.5 megapascals all the way back to the surface deck, strictly limiting the pressure drop rate to less than 10% and allowing scientists to comprehensively study deep-sea life in its native high-pressure state without suffering any structural failure or biological degradation. The rigorous, uncompromising engineering principles required to keep the crushing, lethal weight of the ocean firmly out of a deep-sea submersible share a direct, highly reciprocal relationship with the exact technology used to keep massive, extreme pressures contained within industrial pharmaceutical equipment. The incredible resilience and structural perfection of deep-sea titanium hulls are flawlessly mirrored in the design of the ultra-high pressure chambers heavily utilized by the modern medical industry. Leading manufacturers of medical-grade high-pressure processing units build massive steel systems perfectly engineered to safely, repeatedly operate at up to an astonishing 10,000 bar, pressures that completely eclipse even the very deepest ocean trenches on Earth by nearly a factor of 10. These specialized, highly regulated pharmaceutical chambers are completely defined by their isostatic nature. Just as the ocean exerts perfectly uniform hydrostatic pressure on the exterior of a spherical submersible, these internal chambers apply perfectly uniform multi-directional pressure to the delicate medical objects placed inside them. This incredible structural overlap highlights a deeply fascinating duality in modern human engineering. The exact same metallurgical principles, advanced material sciences, and complex fluid dynamic equations used to forge flawless titanium spheres to protect explorers in the abyss are simultaneously utilized to build impenetrable, hyper-pressurized steel cylinders that aggressively facilitate cold sterilization and total pathogen inactivation in the medical field. By completely mastering the physics of containment and compression, visionary engineers have seamlessly linked the daring exploration of the Earth's deepest, darkest frontiers with the rapid, life-saving advancement of modern healthcare.
The highly controlled, systematic application of extreme pressure has rapidly emerged as one of the most profoundly disruptive and absolutely vital technologies in the modern medical, pharmaceutical, and food processing industries. For decades, the crucial task of ensuring the sterilization of highly sensitive, perishable products relied almost exclusively on aggressive thermal processing, highly toxic chemical baths, or high-energy radioactive irradiation. While undeniably effective at destroying dangerous pathogens, these antiquated legacy methods often come with severe, highly detrimental drawbacks, including the catastrophic thermal degradation of essential nutrients, the permanent alteration of delicate, heat-sensitive chemical structures, and significant, highly publicized environmental hazards. In direct, innovative response to these severe limitations, high-pressure processing, also widely known in the industry as cold pasteurization, has been rapidly adopted as a completely revolutionary, entirely heat-free alternative that relies on the sheer principle of pure, unyielding physical compression to achieve total commercial sterility. In this fascinating process, products are carefully placed into a massive heavy-duty pressure vessel and completely submerged in a liquid transmitting medium, which is most typically highly purified water. Massive specialized hydraulic pumps then systematically elevate the internal pressure to absolutely extreme levels, ranging anywhere from 100 to 1,000 megapascals, which is equivalent to over 100,000 pounds per square inch of continuous crushing force. The underlying biological mechanism of high-pressure processing is brutally overwhelmingly effective, yet remarkably chemically delicate. When dangerous bacteria, aggressive molds, resilient spores, and deadly viruses are subjected to these extreme, highly pressurized atmospheres, the immense isostatic pressure physically and violently compresses the microscopic organisms from every conceivable angle. This sheer, inescapable force thoroughly disrupts their complex internal cellular structures, massively denatures their vital, life-sustaining proteins, and ultimately ruptures the cellular walls entirely, leading to the incredibly rapid inactivation and absolute death of the pathogen. However, because standard HPP operates at very cold or mild ambient temperatures, typically ranging between 5 and 20 degrees Celsius, it completely fails to generate the high thermal energy required to break the incredibly strong, covalent chemical bonds that form essential vitamins, delicate antioxidants, and complex flavor molecules. Consequently, the cellular walls of harmful bacteria are utterly annihilated without changing the fundamental flavor, the physical texture, or the highly prized nutritional profile of the processed product. This highly unique, almost paradoxical capability has made HPP a massively transformative technology in the global food and beverage sector, massively extending the safe shelf life of fresh juices, premium meats, and plant-based foods, while perfectly satisfying massive consumer demand for clean label products that are completely free of artificial, highly processed chemical preservatives. As the technology has rapidly matured, scaled, and proven its undeniable efficacy, the overall scope of high-pressure processing has expanded far beyond the commercial food industry. By the year 2026, a profound, industry-shaking shift is rapidly occurring towards using this exact highly calibrated pressure technology for the absolute sanitization of complex medical implants, sensitive surgical equipment, and highly advanced pharmaceuticals. The primary catalyst for this massive transition is deeply rooted in rapidly evolving, highly stringent environmental regulations and the severe, unavoidable limitations of traditional, legacy medical sterilization protocols. Historically, the global medical device industry relied heavily, almost exclusively on ethylene oxide gas to sterilize heat-sensitive equipment that could not survive an autoclave, such as life-saving pacemakers, complex surgical kits, deeply integrated electronics, and delicate catheters. However, ethylene oxide is a highly potent, highly flammable, and incredibly dangerous carcinogen directly linked to severe, devastating long-term health risks, including vastly increased rates of lymphoid and breast cancers, particularly in vulnerable, low-income communities geographically surrounding commercial sterilization facilities. Consequently, powerful regulatory bodies like the United States Environmental Protection Agency, or EPA, have proposed strict, highly controversial amendments to the National Emission Standards for Hazardous Air Pollutants, NESHAP, drastically restricting the use of ethylene oxide and forcing the massive medical industry to urgently seek safer, highly reliable alternatives to permanently secure the domestic supply chain of critical medical equipment.
Concurrently, heavily relied upon alternative methods such as gamma and X-ray irradiation have proven highly problematic and ultimately unsuitable for the next generation of advanced, biocompatible medical devices. While high-energy ionizing radiation is undeniably effective at killing germs by severing the DNA and RNA molecules present in bacteria and viruses, the incredibly high-energy rays simultaneously cause massive chain scission within sensitive polymers. This brutal radioactive bombardment severely reduces the molecular weight, thoroughly compromises the toughness, and drastically lowers the elongation properties of crucial bio-based plastics, like the poly-L-lactic acid commonly used in modern, highly advanced implants and tissue engineering. In incredibly stark contrast, medical-grade HPP offers a vastly superior, entirely non-toxic, completely residue-free, and totally radiation-free methodology. When absolute safety and total sterility compliance are absolutely non-negotiable, medical-grade HPP units operating at up to 10,000 bar with incredibly precise temperature controls ranging from -20 to +100 degrees Celsius provide highly controlled, flawlessly monitored environments. Due to its unique isostatic nature, the intense pressure flawlessly penetrates the deepest, most microscopic crevices and incredibly complex internal channels of advanced medical instruments without ever compromising their delicate structural integrity, ensuring that complex geometries and advanced polymers remain completely unharmed and functionally perfect. This massive pressure-based paradigm shift is rapidly unlocking entirely new, highly lucrative frontiers in medical research, pharmaceutical development, and advanced patient care. In the highly critical realm of biopharmaceuticals, high-pressure processing is totally revolutionizing next-generation vaccine development. By utilizing extreme, carefully calibrated compression to thoroughly inactivate deadly viruses and dangerous bacteria, brilliant researchers can entirely eliminate the pathogens while meticulously preserving their native, highly complex antigenic structures, a delicate biological feat that is completely impossible with aggressive heat or brutal chemical degradation. This highly innovative approach yields significantly safer vaccines with vastly enhanced, highly targeted immunogenicity. Furthermore, controlled high-pressure environments are rapidly becoming the absolute gold standard for the highly sensitive decontamination of human tissue and bone allografts. Exposing fragile donor tissues to highly calibrated, ultra-high pressure effectively obliterates highly transmissible, deadly diseases such as HIV and hepatitis, while perfectly and meticulously preserving the vital biomechanical strength, crucial elasticity, and structural properties of the allograft. Through the brilliant, highly controlled application of pure, unyielding physical compression, the entire medical industry is aggressively moving into a safer, highly advanced era where absolute, undeniable sterility can be consistently achieved without ever sacrificing the surrounding environment, the health of the community, or the structural perfection of the life-saving medical devices themselves. As our scientific mastery of immense pressure continuously expands, it is rapidly defining the very absolute limits of human engineering and cosmic exploration. The unprecedented ability to fundamentally manipulate the physical world by systematically increasing atmospheric pressure is actively paving the way for massive technological breakthroughs that were, until very recently, entirely relegated to the realm of speculative science fiction. One of the absolute most critical, highly complex challenges facing the urgent, global transition to a sustainable clean energy economy is the safe, highly efficient, and economically viable long-term storage of hydrogen gas. Hydrogen possesses truly immense, undeniable potential as a zero-emission energy carrier capable of decarbonizing heavy transportation and massive industrial sectors, but its exceptionally low volumetric energy density at ambient atmospheric conditions makes it notoriously difficult, highly dangerous, and exceptionally expensive to handle and transport. The traditional legacy approach relies entirely on extreme mechanical compression, forcing the highly volatile gas into massively heavy, highly reinforced carbon fiber composite pressure vessels at incredibly high pressures, ranging from 350 to 700 bar. This antiquated method is heavily flawed and completely unsustainable. Compressing hydrogen to such extremes is highly energy-intensive, incurring a massive penalty that consumes between 15 and 40% of the actual energy stored within the hydrogen itself, and it remains inherently dangerous due to the constant risks of high-pressure leaks, catastrophic explosive failure, and high boil-off rates.
Predicting the rapid, highly disruptive trajectory of the clean energy sector clearly reveals that the absolute future of energy infrastructure lies in advanced solid-state hydrogen storage. An incredibly innovative, highly disruptive approach that utilizes the intricate principles of high pressure and complex physical chemistry to entirely revolutionize how we safely trap, store, and transport immense volumes of energy. Rather than using brute mechanical force to hold highly pressurized gas in a massive hollow steel or carbon tank, solid-state systems utilize highly advanced porous materials, complex intermetallic alloys, and incredibly sophisticated metal-organic frameworks to physically and chemically adsorb hydrogen molecules directly into a highly engineered solid lattice. Pioneering materials companies are aggressively utilizing nano-engineered reticular materials to achieve truly remarkable, unprecedented storage densities at significantly lower, vastly safer pressures. By deliberately designing highly complex crystalline structures with perfectly repeating molecular building blocks, materials engineers can coax neutral hydrogen molecules to spontaneously form highly dense pentahydrogen clusters within the material's microscopic nanopores. These incredibly dense clusters are highly stabilized by the formation of unique, highly directional hexahydrogen bonds, pulling the hydrogen molecules so tightly together that their ultimate packing density brilliantly mimics that of pure metallic hydrogen, a phase of matter typically found only at the extreme, unimaginable pressures at the core of massive gas giants like Jupiter. This brilliant, highly sophisticated manipulation of physical chemistry allows massive MOF systems to store immense commercially viable volumes of hydrogen at a mere 20 bar of pressure, drastically reducing massive capital expenditures, completely eliminating the need for complex, highly failure-prone multi-stage compressors, and providing a highly secure, incredibly high-density energy buffer that is absolutely vital for stabilizing intermittent renewable power grids over long durations. Equally revolutionary, and perhaps possessing even more profound implications for the future of global human infrastructure, is the ongoing, highly competitive scientific quest for true room-temperature superconductivity. For over a century since its initial discovery in 1911, the miraculous phenomenon of zero electrical resistance was inextricably, frustratingly linked to extreme, highly expensive cryogenic temperatures, severely limiting its practical, widespread application in global power generation, perfectly lossless energy transmission grids, and advanced medical imaging devices like MRI machines. However, brilliant condensed matter physicists eventually discovered that what absolutely could not be easily achieved with extreme cold could potentially be forced into brilliant existence with extreme, unimaginable pressure. By aggressively squeezing highly complex hydrogen-rich materials, scientifically known as superhydrides, inside tiny diamond anvil cells to horrific pressures wildly exceeding 100 gigapascals, scientists essentially recreate the crushing, violent depths of massive planets to fundamentally alter the vibrational frequencies of the atomic lattice. These absolutely extreme conditions violently force electron-phonon coupling, miraculously giving rise to undeniable superconductivity at remarkably high near-room temperatures.
As of April 2026, the entire global scientific community is intensely, aggressively focused on achieving this miraculous effect without the highly restrictive need for constant, crushing, multi-megabar force. A genuinely groundbreaking, highly innovative conceptual leap has emerged through a brilliant technique known as pressure quenching, which specifically seeks to achieve highly stable room temperature superconductivity through precisely calibrated pressure environments rather than brute, sustained, permanent force. In this highly delicate, incredibly complex physical process, a multi-component superhydride, such as a highly complex cuprate like HBCCO or a heavily researched lanthanum-yttrium alloy, is carefully synthesized under extreme pressure. Once the precise, highly desired superconducting phase is successfully achieved and verified using advanced synchrotron X-ray diffraction, the material is incredibly rapidly quenched or aggressively depressurized at extremely low temperatures. This incredibly sudden, violent removal of pressure intentionally and permanently generates massive structural defects within the crystal, effectively locking the atomic lattice into a highly unique metastable state that successfully retains its extraordinary quantum properties even after the physical pressure is entirely removed. Utilizing this incredibly advanced chemical and physical choreography, leading researchers at institutions like the University of Houston have achieved staggering, world-changing new records, successfully maintaining absolute superconductivity at 151 Kelvin under standard ambient atmospheric pressure for extended periods. as highly dedicated researchers meticulously add new elemental dopants to these complex superhydrides to chemically stabilize them at progressively lower pressures. They edge ever closer to the ultimate holy grail of condensed matter physics: true, highly stable room temperature, ambient pressure superconductivity. From the colossal, thundering hydraulic presses flawlessly forging the rigid, high-strength skeletons of our modern vehicles, to the microscopic, perfectly clear diamond anvils uncovering the deepest, most complex quantum secrets of the universe, our undeniable ability to squeeze, compress, and manipulate matter entirely defines the bold trajectory of modern human civilization. The deliberate, highly controlled application of extreme pressure is not merely a blunt mechanical action, it is a highly sophisticated fundamental thermodynamic tool that actively allows humanity to completely rewrite the established rules of chemistry and physics. Whether we are bravely descending into the freezing, crushing abyss of the deepest ocean trenches, aggressively stripping deadly invisible pathogens from a life-saving surgical implant without using heat, brilliantly trapping incredibly volatile hydrogen within a microscopic crystalline cage for endless clean energy, or aggressively forcing electrons to flow without any resistance whatsoever, we rely entirely on the undeniable transformative power of compression. High-pressure technology ultimately stands as a shining, permanent testament to our relentless ingenuity, definitively proving that by totally mastering the most extreme, terrifying forces of nature, we can fundamentally, permanently transform the architecture of the future.